Alright, Assalamu alaikum. As you would know, we have a homework that's due tomorrow, and there is a range of questions in the homework that deal with the concept of motional EMF. Now, so far, I would always like to start off with a recapping of the Maxwell's equations because these are central to our discussion. So we have these four equations so far. E dotted with dA integrated over a closed area equals the charge enclosed divided by epsilon naught. We have the Gauss's law for magnetism. B dotted with dA equals 0, where you take this integral over a closed surface area. So these are the Gauss's laws for electricity, for magnetism. And look at the symmetry. You replace E with a B here. You have electric charges, but you don't have magnetic monopoles, so you put a 0 here. Then we also have the relationship that E dotted with dl over a closed path equals 0 if we just have a conservative electric field, but if we also include the effect of time varying magnetic field, it produces a non-conservative electric field. So this right hand side is not really 0. So what is the right hand side? The right hand side is minus the time derivative of the electric flux through an area that is bound by this closed path, and that electric flux is E dotted with dA. So this is the complete form of Faraday's law. So previously I used to write down the partial form of Faraday's law. This is now the complete form of the Faraday's law. This is a closed path. This is an open area which is bounded by this path. And the fourth equation that we've seen so far is the symmetric version of this, which is B dotted with dl. This is a closed path, and this equals mu naught times the current enclosed. This was called the Ampere's law. But remember, so far this is a partial form of Ampere's law. We still have to take into account time varying magnetic fields. Here we have time varying electric fields or time varying fluxes. You can have a constant electric. Sorry, this is B dot D. I'm so sorry. This is B dot dA. You can have time varying magnetic fields, or you could have time varying areas, or you could have both. Whenever you have a time changing magnetic flux, it produces a non-conservative electric field. So these are the four Maxwell's equations that we've seen so far. The first three have been completed, whereas this fourth one deserves some modification. In fact, it deserves completion. It's still partially complete because we haven't taken into account time varying electric fields. We have taken into account time varying magnetic fields or time varying magnetic fluxes, but we haven't taken into account time varying electric fields. So how do time varying electric fields enter this picture? This is something we're going to see towards the end of this class today. But before that, I would like to talk about the concept of motional EMF. Suppose I have a magnetic field that is uniform and it's not changing with time and it's pointed out of the plane of a paper. Now suppose I have a circuit which comprises a resistor, some conducting rails, and on top of this rail I have a conducting rod. and this conducting rod can sail on the rails. It can move on the rails without any friction. All of this is a conductor, I have a resistor here, R. But the point is that this rod can sail on these rails. It can move on these rails, and it moves, suppose, with a constant speed v. Now the question is that can I apply Faraday's law? This is Faraday's law here. Now this is a closed loop. And is the magnetic flux through this closed loop changing with time? Please raise your hands. Is it changing with time? Imtiaz?
Yes.
Why is it changing? Because it's moving. So even though the magnetic field is constant, the area inside this loop, now this loop, I'm just going to denote this with a yellow part. This is the loop that I'm talking about. This is this loop here. So E dot dl around this loop will depend upon the rate of change of magnetic flux to the loop. Since the loop is expanding, in a way the loop is expanding because this rod is sailing, it's moving. The flux through this loop is changing with time, and that will create an EMF or an electric field. Now let's look at the nature of this electric field. This electric field is going to be slightly different from the fields that we've seen so far. But in any case, Faraday's law is going to be valid. It's always valid. So what's going to happen is that I would like to find out, this is simply the induced EMF inside the circuit. Now I would like to find out the induced EMF inside the circuit. Suppose this is really thin, this is thin, everything is thin, this is a resistor, and there is no friction in the motion between the rails and this rod. Can we find out the rate of change of magnetic flux through this area? Could you give it a try, please? Constant speed is v. Suppose this length is L. Suppose this is x, which is a function of time. Could you find out the right hand side of the equation? What EMF is induced? What's the area as a function of time? I've printed your quiz 3. Pick it up. What is x into L? What is the dx here? We need to know where you are putting it. Excellent. Good. Good. Alright, so we need to find the EMF. The EMF is given by minus the time derivative of the flux through this area. Now V is a constant. The total flux through this area is B into this area. B is pointing out, the area vector is also pointing out. So the local dot product is 1. The cosine theta is 1. So every time the field is pointing out, the area vector of this loop is also pointing out. So I don't have to worry about the angles. I can take the constant B and the area is simply V into this X. Now V is a constant, B is a constant, L into X. So L is a constant, B is a constant, the derivative of X is simply the speed. Hence the EMF is given by minus BL, the derivative of X, which is V. And this gives us E dotted with DL around the closed path. Now if this is an EMF that is induced inside the circuit, a current may flow because this is a closed path. So what's the direction of the EMF and what's the direction of the current? What should be the direction of the current? Speak in English, it's going to be clockwise, because that clockwise current will produce a magnetic field that's pointing into the plane of the paper, because as this circuit stretches, the flux threading this area goes up. So the current would like to go in a path such that it produces its own field which is opposite to the change. So it produces a magnetic field that's pointing into the plane of the paper. And this would be the proper direction of the current. So the current is going to flow through all of this circuit. This current I will be given by this EMF divided by R. This is an induced current. And when this current passes through this resistor, it can heat up the resistor. It will dissipate power inside the resistor. And the power dissipated in this resistor is going to be I square R. The power in the resistor is going to be I square R. So you can light up this bulb, if it were a bulb, using this motion. So a conductor that is moving inside a constant magnetic field can also produce an EMF. And that EMF can drive a current to the circuit, and it can deliver useful power. You can heat up your electric furnace, you can glow a light bulb, or you can do useful work with this power that is delivered. Now where is this power coming from? Is it coming from the magnetic field? Is it coming from the electric field? Where is the source of this energy? For that we need to have a closer look at this concept of motional EMF. And if there are any charges that are induced onside this circuit. So any questions up to this basic concept of motional EMF? Higher the speed, higher will be the EMF. Higher the magnetic field, higher will be the EMF. Now, is this a non-conservative electric field here? That's something we really need to explore. So what I'm going to do now, I'm going to look at this simple example with a more acute eye, with a more hawkish vision. I'm going to look at it more closely. So now I would like to look at motional EMF seen closely. I would like to go a bit deeper so that I can understand the exact nature of this effect. And that's what physics does. It really goes beyond the curtains. It unveils what is apparent and tries to go into the depth and see and unravel what's going on at a more deeper or fundamental level. Now forget about this closed circuit. Suppose I have a piece of wire, a rod, that is moving with some speed, v, which is a function of, could be a function of time. And this is a cylindrical rod and it has a length L. And there is a uniform magnetic field in the background which is pointing out of the plane of the blackboard. And it's constant. Now we have mobile electrons inside this conductor. So let's focus our attention on a single electron. Now when this electron is moving with the speed v towards the right in a constant magnetic field, what's going to happen to this electron? Will it experience a magnetic force? Yes. So what's the direction of that force? Downwards. Q, V, cross with B, but that's for a positive charge, so the magnetic force will be actually upwards. So if this were a positive charge, the force would be downward. This is a negative charge, so the magnetic force would be upward. QV cross B. So Q, the velocity is here, field is outside, so the force points downwards for a positive charge. If Q is negative, the force is going to point upwards. So the magnetic force on this electron is going to point in the upward direction, Fm. Now as this rod moves, all of the electrons inside the rod are going to experience an upward magnetic force. That's the Lorentz force. Remember, this Fm is simply given by Q, V crossed with B. Here the charge on an electron is negative, so you have minus EV crossed with B. This is the magnetic force. Now when the electrons move upwards because of this magnetic force, they're going to accumulate here and they have nowhere to go. They can't jump off the surface of the conductor because the energies are not high enough and there's no conductor in between. Everything here is air. So the electrons will start depositing on the top end of this conductor as this conductor is traversing the magnetic field. Correct? So electrons will deposit here, which means that this end will get a negative charge, and negative charge will be depleted from the bottom region because the rod as a whole is electrically neutral. So these negative charges mean that there is an accumulation of positive charge here or a depletion of negative charge here. Now what does this charge separation result in? Will it produce an additional electric field? What's the direction of the additional electric field and the force on an electron? So the field is going to point in the upward direction. What's the force on an electron going to point in? Downwards. So now if I take the electric force on this electron, Fe, that's going to point in the downward direction because of the accumulation of these charges. Once again, feedback is taking place. As we move this conductor through this static magnetic field, V, static, electrons are being pushed towards the top end of this conductor and they're going to be depleted from here. So this requires a positive charge and an internal electric field is set up because of the sheer motion of this conductor inside a magnetic field. Now when equilibrium is established, both of these forces are going to be equal because as more and more electrons are deposited here because of the force, this electric field builds up and the electric forces build up. At one point, both of these forces join hands. They become equal in magnitude, though opposite in direction. And when that stage is reached, the amount of charges on the top and the bottom surfaces remains constant, remains steady. And this rod achieves a state of equilibrium. Equilibrium really means that this electron experiences no force. And this conductor can keep on moving with a constant speed. So nothing is accelerating. There's no net unbalanced force on anything. That's a state of equilibrium. Now you have a conductor. It's in equilibrium, but still there exists an electric field inside the conductor. So now this is a complete departure from what we've already seen. What we've seen previously in electrostatic conditions is that an electric field cannot exist inside a conductor which does not carry a current. But here, an electric field does exist inside a conductor, and yet it does not carry a current. Because we've now introduced magnetic fields, and we've introduced motion inside a magnetic field. So here, an electric field exists inside the conductor without the flow of current. So even in equilibrium, fields can exist inside conductors whenever you have motion inside a magnetic field. Now this situation of separation of positive charges and negative charges is reminiscent of a device that we use in circuits. What is that device? It reminds us of a device. We've already seen that device plenty number of times. It's a which is called a battery. This is simply a battery here. Now this battery, in a battery what we have is a separation of charges. A capacitor can momentarily act as a battery, but when it drains its current, it's no longer a battery. So in a battery, we have a separation of positive and negative charges. So a battery is simply two plates. One of them acquires a negative charge, the other acquires a positive charge. And there has to be some mechanism which transfers charge against the field gradient. One possible mechanism is a conveyor belt. A conveyor belt carries a belt which is driven by a pulley. This pulley moves, it picks up electrons from the positive charged plate and transports them to the already negatively charged plate against the field gradient. So you supply external energy with a motor that moves this pulley, and it conveys electrons against the field gradient. You see, an electron here will experience a force in this direction, but you're applying external force to an external agent so that it moves against the electric field that's set up inside the battery. Exactly in this scenario, you are creating a separation of charges through motion, mechanical motion inside a magnetic field. So this thing acts like a battery, and it indeed produces a separation of charges. So now let's use this as a battery and connect it to a circuit. That's exactly what we've done here. So in motional EMF, this rod is starting to act like a battery. In a battery, energy, in a chemical battery, energy is supplied by the chemical reactions at the electrodes. Here the energy is supplied by the motion of this conductor inside a magnetic field. And we'll have a closer look at this in a minute. So this moving rod inside a conductor acts like a battery, and this battery can be connected to a circuit, and it can drive current through the circuit, and you can do something useful with that circuit. Alright, now let's connect this moving rod on which this charge separation has accumulated inside a circuit, and this is precisely the circuit that we're going to talk about. Again, there is a field pointing out, constant field, uniform field. An accumulation of negative charge here, accumulation of positive charge here. Speed is v. Could be a function of time. Now this conductor is being moved, positive charges accumulate here, negative charges accumulate here. So I'm positing or proposing that this acts like a battery. Now let's look at the electric fields that are set up inside the circuit. What's the direction of the electric field inside the circuit, inside the wires? If this were to be a battery, there is a Coulombic field that is set up now, because charges exist on the ends of this wire. It's not a non-conservative electric field, it's a conservative electric field because of the presence of these charges. It just acts like a battery, a wire connected to a battery. So what's the direction of the electric field inside this conductor? Sam? Clockwise, right. So this electric field is going to point inside the wires in this direction. This is the direction of the electric field. If this is a thin piece of wire which acts like a conductor, the field inside the conductor will be really large because it's an insulator, really. It's a resistor. So this is the direction of the electric field inside the circuit. What's the direction of the electric field inside this piece of rod? It's going to be supposedly in the wrong direction. That's what happens inside a battery. Inside a battery, the electric field is apparently in the wrong direction. So that's why you have E dotted with DL inside a closed circuit. If this is a Coulombic electric field, this actually goes to zero. Because if you go around this circuit, the potential drops, then the potential decreases. Because the electric field is in the wrong, supposedly in the wrong direction inside the battery. So the electric fields turn out to be in the correct disposition inside this example. They're in the correct direction. Inside the battery, they are supposedly from positive to negative, the plate, so it's supposedly in the opposite direction. So if an electron has to be transported from this end to this end, it has to move against the electric field. It has to move against the forces of the electric field. So this is exactly analogous to a situation of a battery that has a wire connected to it. Yes? Can we please speak up? In that? Right? Because here, this is positive charge here, negative charge here, so this is the direction of the electric field inside the rod. Okay? This is the direction of the electric field inside the rod. Okay? Or the battery. This is just acting like a battery. Okay? Positive charge, negative charge, field points from positive to negative charges. Alright? So here, as you go around the field, you're moving with the field, parallel to the field, but here you're moving against the field. So one causes a drop in the voltage, the other, this path causes an increase in the voltage. And remember, this is a Coulombic field. It creates a separation of charges because of the motion of this conductor inside the static magnetic field. And this charge will actually dilute itself on the surface as we've conventionally seen already. Okay? So the charges will dilute themselves on the surface of this current carrying conductor. And this is just the battery. Now the question is that the EMF of this battery is actually given by, its magnitude is given by V times B into L. This is what we've already derived here. But we also know that the EMF is given by the work done by the non-conservative forces. So what's the non-conservative force that has actually created a separation of charges here? What's the force that has created this separation of charges? It's the magnetic force. So this non-conservative force is simply the magnetic force. So the work done by the non-conservative force is F mag into this distance, L, divided by the charge on an electron, the per unit charge. This is our definition of the EMF of a battery. The work done by non-conservative force divided by the charge here for a simple battery, it's the amount of work that is done by this pulley in moving this electron from the positive to the negative plate divided by the charge of the electron. We've already seen that when we were discussing batteries. So this is the EMF generated inside the battery. It's F mag L over E. But in equilibrium, this F mag, this magnetic force, equals the electric force. Correct? So what is the magnetic force? The magnetic force F mag is given by the charge on an electron VB. QB cross B. If you look at this equation, it's simply going to be EVB. So I insert this value in here, I get VBL. So from an alternative route, by looking at the EMF of a battery and using the magnetic force as the non-conservative force that creates a charge separation, we get the same EMF as we've gotten from the Faraday's law. Now, a really interesting observation. Any questions at this juncture? What we've seen, we have a rod, we move it through a magnetic field with some speed, it develops a charge separation, it becomes polarized, it starts acting like a battery. We connect that battery to a circuit, current flows. The EMF of that battery can either be given by Faraday's law, and the same EMF can also be determined by looking at this definition of the EMF of a battery, which is really the work done by the non-conservative forces inside the battery divided by per unit charge. Yes, you had a question.
When the electrons do flow through the rod,
before the circuit is connected?
No, after it's connected.
Right.
And it's moving as well. Won't there be a force on the rod?
Exactly, that's my next point here. Suppose it's a beautiful question. Now a current is flowing through this circuit. Let's look at the direction of this current. Excellent question. Now this is the electric field inside the wire. So what's the direction of the conventional current? Bilal? It's going to be parallel to the electric field here. So current is going to flow like this. And it's a steady current. So it's going to flow in a clockwise path. This is also in accordance with Faraday's law or Lenz's law. This is the direction of our current, I. This current can do some useful work here. It can glow a light bulb. So the electric power can be dissipated here. It's available for us in a useful fashion. And that power is I square R watts. This amount of energy is available per unit time to do something useful. Now the point is that when a current flows through this conductor and there is a magnetic field, what's going to happen to this conductor? Is it going to experience some force, some mechanical force? Whenever you have a current carrying conductor placed inside a magnetic field, will it experience a force? हमने तो डेमोन्स्ट्रेशंस भी देखी हैं कि एक मैग्नेटिक फील्ड है, उसके पास से एक करंट कैरिंग कंडक्टर गुजर रहा है, वो डिफ्लेक्ट होता है, it experiences a force. So what's the direction of that force? If the current is going downwards inside the rod and the magnetic field is pointing outward, what's the direction of the force? Towards the left. So IL crossed with B. I is downward, field is outside, the force is pointing towards the left. So a force acts on this rod. Let's call this F on the rod. That force, F on the rod, its magnitude is I, L crossed with B, multiplied with B, which is the constant field that's pointing outwards. ILB. Now let's look at this rod. This rod is experiencing an unbalanced force towards the left. Therefore, if you would like EMF to be constant, which means that the current through this circuit to be constant with time, you would like the speed to be constant. Now if you want the speed to be constant, you cannot have an unbalanced force on side this rod. Therefore, in order to keep the speed of this rod constant, you have to supply some external force. In order to keep this rod moving with uniform speed, you have to apply an external force on the rod in this direction, F external, to keep this rod in equilibrium so that it keeps on moving with a constant speed, so that it delivers a constant power to the resistor, or it keeps its EMF constant. Hence, nothing comes for free. If you would like to make current flow through this device so that it lights up or does something useful, you have to supply energy externally. Externally, that energy applied means that you have to apply an external force, and that external force must be actually equal to this ILB. So the external force must equal this. You have to apply a constant supply of energy so that a constant current flows through the circuit. Otherwise, if you start with the speed and then let everything go, this force will actually decelerate this rod so that it will eventually come to a halt and the EMF is going to drop to zero. So if you would like this battery to act as a constant source of energy, you would like to make it move, you would like to apply an external force which exactly balances out the force on the rod due to the current that's flowing inside. And this is the source of energy. This is a mechanical battery. This mechanical battery has to be continuously run with an external source. A chemical battery is continuously run by the chemical reactions inside the voltaic cell. But when the cell is depleted, which means that the electrolyte becomes so dilute because of precipitation that the battery runs out. So you really have to replenish the battery chemicals inside a battery. Likewise, you have to continuously supply energy to this mechanical battery so that it becomes a source of an EMF and delivers a current. And that external field force has to be equal to the force on the rod. But the force on the rod is ILB. But what is I? I is simply E over R. The EMF into R, LB. But what is the EMF? It's VBL, B L squared, B squared over R. So this is the amount of external force that needs to be done, that needs to be continuously applied to this circuit so that a constant current flows through this pipe. Now remember, the power dissipated inside this resistor is I squared R. What's the power done, or the power that is input to this circuit? The power that is input to this circuit is given by the external force that is applied into the speed, right? Power is force into the speed. So the power that is delivered into this circuit by mechanical means, the external power that is delivered to the circuit is given by this, Fx into V. Alright, so if I look at this, Fx is ILB into V. But what is LBV? It is the EMF. What is this? This is I into IR. But if you would like this condition to be satisfied, IR is the total voltage drop across this path. That must equal the EMF of the battery, because everything else doesn't have a resistance. So this IR is in fact the EMF of the battery. The power delivered to the resistor, all of that power is coming from the external power supply, the external mechanical generator which is moving this rod. So the power is not coming from the magnetic field. The magnetic field cannot do any work. Remember, a uniform field never does mechanical work. A uniform magnetic field can never do any work. All of the power that is being delivered to this resistor is actually coming from an external source. That external source is required to keep on moving this rod with a constant speed. That power has the same magnitude as the power delivered to the resistor, and energy is conserved. You put in power through an external means, you move this conductor, and for that you have to apply an external force. That power equals the power dissipated inside the resistor. So power in, power out. All the power that's delivered to the resistor, you have to apply it. The magnetic field doesn't help you. The magnetic field helps you only in a very tortuous way, in a very complicated way. The magnetic field is producing an electric field. That electric field is a result of the charge separation. That makes a current flow. The current is flowing through the conductor. That produces a force on the rod. In order to balance out the force on the rod, you have to apply external energy. This is how things work. It's a long, tortuous path. It's a long, tortuous logical argument. Here I would like to take a brief pause so that all of this sinks down into us. And then we'll come up with another interesting example. Remember, a uniform magnetic field cannot do any work. Look at this. F equals QV crossed with B. This is the velocity and this is the magnetic field. This is the magnetic force. The power delivered by the magnetic force is Fm dotted with V. This is the formula for power. Now since Fm is normal to V because of the cross product, the dot product of Fm with V is always 0. So the magnetic field, the uniform field on its own can never do any magnetic work. It cannot do work. Here we've seen that all the work that is being done, the energy that is available to us is coming from an external source. Because an external source is required to keep on moving this rod with a uniform speed. Let's look at another example. And that example is that of a falling rod inside a magnetic field. Now let's suppose I have a rod which is horizontal and it's conducting just a piece of wire and it falls inside the gravitational field. I just make it go inside a gravitational field. So initially the acceleration due to gravity downwards is g, and the velocity that's downward could be a function of time. So this rod is falling down. Now I have electrons inside this rod. Let's consider a single electron. Now this falling rod can act like a battery, which means charges will be developed on its ends. A charge separation is going to take place. Now there's no chemical reaction taking place, it's just sheer mechanics. Now, could you tell me what the direction of this charge separation is going to be? There is a field, by the way. That field, suppose it's still pointing out of the plane of the black hole. You need that field, that magnetic field. It's a uniform field. Now what's the direction of the polarity that develops on this moving rod, falling rod? The magnetic force is towards the right. Let's see. Velocity is downwards, field is outward. On a positive charge, the force is to the left. So on a negative charge, the force is going towards the right. So electrons will accumulate here. The magnetic force Fm is pointing in this direction on an electron. But then this will become depleted of electrons, so it will require a positive charge. This means an electric field is going to be set up in this direction from left to right, but the force on an electron is in this direction, Fm, Fe. In equilibrium, this force, remember, this force, देखो, बड़ी अहम बात है, this force depends upon the speed. So if this object is accelerating, this force is going to go up. But when this force is going to go up, the charge separation is going to go up. When the charge separation goes up, the electric field is going to go up. So electric force is going to go up. And at one point they will touch base. They will be at par with one another. And that will be a situation of equilibrium. Okay? So an EMF is developed. That EMF will be equal to B, V, which is a function of time, into L. Remember, this EMF is a function of time. The length of this rod is L. How do I know that this EMF develops? Quite simple. You look at the magnetic force, Fm. Fm equals, its magnitude equals E, V, which is a function of time, into V. In equilibrium, this must equal E into the electric field that's set up. Okay, now let's look at the electric field. The electric field that's set up, E, is VB. But what is the potential difference across the ends? The potential difference across the ends, which is called the EMF, it's called nothing but the EMF, equals this electric field into the length, the charge separation, which is L. So this is VBL. This V is a function of time, hence this EMF is also a function of time. So an EMF is developed because this rod becomes polarized as it falls through this magnetic field. Now what I would like to say, what is the acceleration on this rod? Now what I do, I would like to connect this falling rod to a circuit. So I have rails here, and the motion is frictionless. So if this rod falls down, it just brushes the rails. So it is not impeded by the rails in any fashion. It just brushes down the rails as it falls down. And here I have a resistor, R. Once again, I have a magnetic field that points out. It's the same scenario, but now I'm connecting this rod to a circuit. And what I'm interested in is finding the acceleration. The first point is that this acceleration will not be equal to the acceleration due to gravity. Let's see why. Suppose this rod is falling down, so positive charge develops here, and EMF develops, in other words, and negative charge develops here. Now this is an EMF. That EMF is given by this expression. This, by the way, is time dependent. This depends upon time because of the possibility of acceleration. Now if this is the EMF, there is a current flowing through the circuit. What's the direction of the current? Clockwise? Clockwise is going to flow like this. I is going to flow like this. To the rod, it's going to flow like this. Now, due to the flow of current inside this rod, a mechanical force is going to act on this rod. What's the direction of the mechanical force? Upwards? I, upward. The mechanical force on the rod is upwards. F of rod. F of rod is upwards. The weight is acting downwards. F of G is acting downwards. Now you have two forces acting on this rod, and there's a net force that acts on the rod. That net force, F net, equals Fm of F due to the gravity minus F on the rod. The magnitude of F net is going to be mg minus F on the rod. Now F on the rod is I L B G. देखो करंट इस तरफ जा रहा है और फील्ड आउटवर्ड है, IL क्रॉस विद B. Okay. Now this is the magnitude of the net force. So what's the acceleration of the net force? It's going to be on this rod is going to be G minus I L B over M. Quite interesting. Look at this. If it were free fall, the acceleration would be simply G. But now what's going to happen is that the acceleration is going to decrease from the acceleration due to gravity. This is like damping. This is magnetic damping. It's not going to accelerate with G, with 9.8 meters per second square. It's going to accelerate at a smaller rate. The acceleration will be impeded. Now you haven't applied any hydraulic brakes or pneumatic brakes, or there's no friction here, but this rod is going to brake itself. This is magnetic braking at work because a current flows through this rod, and that current is inside a magnetic field, so a mechanical force acts on the rod. Okay, so this is the acceleration due to gravity, and this is the net acceleration of this rod. Now this current depends upon the EMF. We know that the current depends upon the EMF. The EMF is a function of time. BBL. V is a function of time. PL. This is the EMF divided by R. This gives me the current. Alright? Now there is some acceleration. It's less than the acceleration due to gravity. But as there is some acceleration, this V goes up. When this speed goes up, the current goes up. When this current goes up, this term goes up. And when this term goes up, it can eventually reach a position where this acceleration, this is also an acceleration, its dimensions are of acceleration, will become equal to the acceleration due to gravity. And when that happens, the net acceleration in equilibrium equals 0. So a particular speed is acquired, or the terminal velocity at which the acceleration to net acceleration goes to 0. Which means that this upward force on the rod becomes equal to the downward force. This is constant. It's mg. It's not going to change. But this force on the rod is going to go up if the current goes up. Because this F rod is simply I, L, B. B. But this I depends upon the EMF. Right? This EMF. EMF, which is a function of time, PL over R. But this EMF depends upon the speed. V. V square L square over R. Now, when the speed goes up, this force on the rod goes up. Initially, when everything was at rest, there was no force on the rod, no upward force on the rod. But this force is going to build up. It builds time as the speed goes up. Eventually, these forces will become equal. And when this becomes equal, the acceleration would become zero. It's just like a paratrooper. A paratrooper is falling down from an aeroplane. It is accelerating, but then he has a parachute that's opened up. So that parachute gives you an upward air resistance. Eventually, a terminal speed is reached when the upward air resistance becomes equal to the acceleration due to gravity. The upward air resistance goes up because the resistance is proportional to the speed. The speed goes up because of the initial acceleration. So eventually equilibrium is reached when the paratrooper gradually glides down with a constant speed called the terminal speed onto Earth. Exactly the same scenario is happening here, but we don't have any air resistance. It's just that we place the falling conductor inside a uniform magnetic field. And we can find out that terminal speed. If this is zero, then it really means that this force on the rod becomes equal to the weight. So the terminal velocity into B square L square over R equals mg. So the terminal speed equals mg R over B squared L squared. So this is the eventual terminal speed that is achieved by this falling rod. Now if you look at the power delivered to the resistor, the power delivered to the resistor is I squared R. Correct? Or EMF squared over R. It's the same thing. The EMF equals V B squared L squared over R. So in equilibrium, I can put the terminal velocity here, Vt squared B squared L squared over R. In equilibrium, this is the power delivered to the resistor. Vt B squared L squared over R. Correct? You got a question?
So this terminal velocity equal the terminal velocity that we would obtain if we had flown it from a high school and around the accelerated.
No. Then you have to take into account the acceleration due to gravity. There is no magnetic field. There is a different phenomenon at work here.
So the terminal is equal.
No. Do you understand this concept of the terminal speed? Why do we have a terminal speed? The acceleration is lower than the acceleration due to gravity, which shows that there is some kind of magnetic friction or magnetic viscosity or magnetic braking or magnetic damping. All of them are the same thing. Now what I would like to argue is that this power delivered to the resistor, where is that power coming from? Is it coming from the magnetic field or not? Now the power delivered to the resistor is I squared R, which is also equal to EMF squared over R. Now the EMF is, when equilibrium has been established, is VBL. Now I am taking the terminal speed. So in equilibrium, this is the power delivered to the resistor, Vt squared V squared L squared over R. But what is V? If I look at Vt from here, if I insert the expression in here, I will obtain m squared g squared r squared Okay, m squared, g squared, r squared, b squared, l squared squared. But then I have a b squared, l squared here over r. I have m squared, g squared, r over b squared, l squared. This is the power delivered to the resistor. Where is this power coming from? Coming from? It's coming from the force of gravity, the gravitational potential energy. So let's look at the force that is delivered by gravity. The power that is delivered by gravity equals the force of gravity, which is mg, into the terminal velocity. The power is force dotted with the velocity. So this terminal velocity, once again, is given here. So I have squared here, r over b squared, l squared. The power delivered by gravity equals the power that is dissipated inside the resistor. So all of this power is being delivered by the force of gravity. The magnetic field is not doing any work. All the work is being done by gravity. I would like to bow down my head in the aesthetics of this argument. So beautiful. You're delivering power to a resistor, which means you're getting energy, useful energy. That energy is coming from gravity. And you're going through the route of a magnetic field. The magnetic field is acting like a vector. It's transmitting energy from one form to another, but it's not participating in the energy. It's not delivering energy on its own. It's acting like a handmaiden, like a servant. So all of the power that is delivered to the resistor is coming solely from gravity. The magnetic field is just a springboard. It's just helping us in the way. It's just showing us the direction. Yes. Is this process efficient? Alright, so suppose you need 1 watt of power in a resistor. You can do a numerical calculation. You need 1 watt of power. You have an object of say half a kilogram that's falling down, or say any resistor you take, a 1 kilo ohm resistor, length, reasonable length 1 meter. You can work out the values and see whether the magnetic field that is required to obtain 1 watt of power is technologically feasible. But the problem is that if you work out this calculation, the magnetic field that is required is really, really large. Or you need really, really large, long conductors, or small resistors, or massive conductors to get a substantial power. So you'll have to work out these, but it's an inefficient process because there's also friction. When this rod is falling down these rails, there is friction between this rod and rails. Now I would like to highlight an effect, a subsidiary effect in the last 10 minutes, which is of paramount importance, and that is called the Hall effect, and it is related to all of this. Alright, what we've seen, please note my words carefully. Khamoshi se. When I have a conductor moving in a uniform magnetic field, it becomes polarized. Charges separate out on the ends of this conductor. as a result of which that conductor can act like a battery, which when inside a circuit can deliver useful power. That power is, by the way, not coming from the magnetic field itself, rather it's coming from some external agent that is supplying power. The invisible hand may be of gravity, or the invisible hand of a motor that is moving the rod with a constant speed inside the magnetic field. It's coming from some invisible hand, and you'll have to figure out that invisible hand. Alright, here I'm using the word invisible hand metaphorically. Alright, so please keep that in mind. Now I would like to talk about the related effect called the Hall effect. Some students have already done an experiment on the Hall effect in the laboratory. In the Hall effect, nothing moves, but still you have a separation of charges. Suppose I have a conductor or any material, a semiconductor or anything, which has a certain width W, a certain thickness T, maybe a length L, and it has mobile charge carriers. Suppose it has electrons, which are the mobile charge carriers. It's a conductor, in other words. And I make current flow through this wire, through this piece of wire. So current comes, goes in, comes out. And it's a steady current. And if this steady current is to flow, what's going to happen is that electrons are going to move with the drift velocity. Now all of this is placed inside a uniform magnetic field that's, say, pointing upwards. This field is pointing upwards. So it's normal to the current density. The current density is horizontal, the field is upwards. Now since there is a current flowing through this wire, which means that if I consider an electron, it has a drift velocity. What's the direction of the drift velocity of the electrons, of the sea of electrons? Towards the left. So this is the direction of the drift velocity of the electron, Vd. Because this is the direction of the conventional current. Alright, now we have the drift velocity of electrons. What's going to happen to these electrons? Will they experience a magnetic force? Yes. What's the direction of that force? Outward, out of the plane of the blackboard. So what's going to happen is that if I look at this piece of, so if I look at this piece from here, if I observe from here, from the top, I can draw this diagram from the top. This is T, an electron. This is its drift velocity. The field is coming out of the plane of the blackboard. And as you correctly point out, the magnetic force is downwards. It's out of the plane of the blackboard. So this side, the side that faces us, develops a negative charge because the electrons, as they are drifting from left to right, they are spiraling downwards under the action of this magnetic force. So this electron will actually move downwards under the action of this force. So this surface will develop a negative charge, or this surface that's facing us will develop a negative charge. But the other side will be depleted of negative charge, so it will develop a positive charge. So at the back we develop a positive charge. At the back end, here. But once again, so now we have a charge separation. That charge separation is arising not because of motion, it's arising because a material is conducting an electron and it's placed inside a magnetic field. This charge separation creates an EMF. Once again, it's called the Hall EMF, and this effect is called the Hall effect. It was discovered in the 1870s by Hall, and in fact it has seen a resurgence in the research community, Batini. Currently, there is a huge plethora of work that is being done on the Hall effect and its modern version, the spin Hall effect, the fractional Hall effect, the quantum Hall effect, the anomalous Hall effect, and so on. And there are several Nobel Prizes that have been given of modern incarnations of the Hall effect. So this voltage is developed. Now, feedback is always chasing us. Because of this separation of charges, an electric field is going to be set up inside this material. And what's the direction of that electric field? It's going to be downwards. That will apply an electric force on the electron. What's the direction of that force? Upwards. So eventually, as more and more charges accumulate, this electric field grows up, and at one point is reached which is called equilibrium, at which these forces become equal in magnitude. What we would like to find out is how much is this EMF, how much is this voltage, and then I can connect another circuit to these ends and make something useful out of it. I can connect it to a voltmeter, it will give me a voltage. I can connect it to electric light bulb, the light bulb will glow if the voltage is sufficiently large enough. So how much is this EMF here? In equilibrium, Fm, the magnetic force, which equals EVB, I'm talking about magnitudes here. This must equal EE, which means VB equals capital E. Remember, this is the drift velocity of electrons. So VdB equals E. But E is simply the Hall voltage that is developed. I call it VH. Divided by, which length would I use? T or W or L? Which length should I use for this voltage? T. Good. T. This means the Hall voltage VH is VD VT. But the drift velocity is difficult to calculate. So what I know is the current. So is the drift velocity related to the current? Yes, it is. And what is the relationship? Current I equals the charge carriers per unit volume into the charge on a single carrier ME into VD into the cross-sectional area. What is the cross-sectional area to which the current is flowing? What is the area? W into T. W into T. This makes my VD equal I NE W into T. Now I insert this in here and I obtain I B N E W. This is the Hall voltage. The Hall voltage depends upon the current, the magnetic field, inversely dependent on the charge carrier concentration and the charge on a single charge carrier and the width of the sample. I can use this device, I can put a voltmeter here. If I were to put a voltmeter here, I can measure the Hall voltage. In other words, I fix a voltmeter to the front end and to the back end. And with this voltmeter, I can determine magnetic fields. So I can use this device to detect and determine magnetic fields if I know the current, even if I know N, E and W. I can use it to determine currents. So if I have power transmission lines and I would like to find out the field or the current due to that line, I can measure the hall voltage of a device that is appropriately placed near that transmission voltage. So this hall sensor can be used as a sensitive sensor of currents, magnetic fields, but it can also be used to determine the charge on a single charge carrier. If these charge carriers were holes instead of being electrons inside a semiconductor, the hall voltage will be opposite in direction. So I can determine the type of charge carriers, whether they are holes, whether they are positively charged carriers, negatively charged carriers, whether I have an N-type material or a P-type material. But the last beautiful thing that I would like to talk about is that if you have this material here and a current is flowing through this material, once again a force is going to act, a mechanical force. So if current is going like this, field is upward, there's a force, a mechanical force that is acting on this device that is in the downward direction. So if I look at this figure, this force is in this direction. Mechanical force. Because a current carrying conductor placed inside a field experiences a force. Now what's the origin of this force? We've talked about these forces, but what's the origin? The Hall effect tells us what the origin is. This material is comprised of positively charged ionic cores and electrons. In equilibrium, what's the net force on an electron? एक इलेक्ट्रॉन पे कितनी फोर्स एक्ट हो रही है in equilibrium? Zero. The electron does not experience any force because of equilibrium. But what if I consider a positively charged ionic core? Of course there are positively charged ionic cores here as well. Will this ionic core experience a force? Yes, because there is an electric field that's downwards, that's out of the plane of the blackboard here. This positively charged core experiences a force due to the unbalanced electric field. It does not experience a magnetic force because it's not moving. It, however, experiences an unbalanced force of electric origin. That unbalanced force acts on these positively charged ionic cores, and since those cores form the lattice or the structure of this rigid wire, the wire itself gets a kick. So the wire moves inside the magnetic field because of unbalanced forces which are of electric origin, which can be taken to be a side effect of the magnetic force, and which causes the conductor to get a kick inside this magnetic field. So the forces on conductors arise out of electric effects, which are described by the Hall effect. Alright, best of luck for your quiz on Friday, inshallah. Thanks a lot.